backbones, you're going to get hydrogen bonding between the backbones. Tertiary structure is R group interactions. So polar, nonpolar, hydrophobic, philic, charged, non-charged, whatever it is, that's your R group interactions. R groups can interact with each other and with the substrate. So R groups help pull in the substrate. Quaternary structure is if you have multiple polypeptide chains. So if I have 3 N-termini, how many polypeptide chains do I have?
3.
3. How many genes are responsible for making that?
3.
There we go. How many C-termini do you have?
3.
3. Excellent.
Better be given.
Okay, some people don't necessarily believe me, so talk to each other.
I got Yeah.
How many N-termini? 8. How many C-termini? 8. How many genes? 8. How many mRNAs were made? 8. 8 transcribed, 8 produced. There we go. Nothing tricky here. Subunits are one polypeptide chain. Residues is an amino acid. So I have 8 subunits, therefore I've had 8 polypeptide chains. What structural levels do I have interacting here? All. I have primary structure because I have NCC. I have secondary structure because I have hydrogen bonds between the backbones. Tertiary structure we have R groups. And quaternary structure because we have multiple
polypeptides.
There we go. 8 subunits, 8 N-termini, 8 8
genes,
8 transcripts. Life is good. It's 8. Where was this protein assembled? Talk to sure. Where was this assembled?
Where was?
Where was this assembled?
Oh, in the ribosome, or in the ER.
Is this the mRNA?
Where was this assembled? Rough ER. Nice job, rough ER. The individual polypeptides were built by what? Then ribosomes. The multiple polypeptides were assembled by the rough ER.
Rough endoplasmic reticulum.
Hey, Dr. Sher.
Primer?
Yeah, this is primary because that's NCC, unrelated to hydrogen bonds. Secondary structure is hydrogen bonds, so I don't think any other structures can form.
Yeah.
If I destroy the hydrogen bonds, will I destroy quaternary structure?
Yes.
Yes. Will I destroy tertiary structure?
Yes.
Will I destroy secondary structure?
Yes.
Will I destroy primary structure?
No.
No, because that's peptide bonds. What are proteins? Everything. Proteins do all the function, okay? So they're going to make the enzymes. That's what we're going to construct today. They give you your structure. They allow for movement, okay? Actin and myosin as your proteins. Membrane channels, molecular carriers, signal molecules, everything down to your hemoglobin. What molecule, what protein did I just show there that had 8 subunits? Anybody know? That was hemoglobin. 8 subunits, therefore each one has a heme product. And they can do anything. So proteins are literally everything and anything, and their structure dictates function. So I talked to her. Reread the question.
All of it? Does it? A protein function dependent upon its primary structure? You think it's true? I put false because I thought it depends on the structure, so the structure doesn't include.
If you take away quaternary structure, will it work? No, therefore this is false.
Oh, okay.
I put true, but I thought, yeah.
Organization dependent on the protein's primary structure.
I'm gonna say true. I would say true.
All right, talk to her.
I don't know. I think they do depend.
Well, secondary structure is only dependent on backbone, though, which is unrelated to the R group.
I think it's like hypothesis, which is like this one.
This is true or false? This is true.
Oh, I was right.
All higher levels are based on your NCC. If I change out my amino acid, I change the shape. So our 8 subunits to come together to form that hemoglobin forms this beautiful shape. I change one of the ones that are hydrophilic to hydrophobic, and what happens? Now you have sickle cell. That's it. One R group changed from hydrophilic to phobic, and you change the shape. It goes from round to sickle shape. That's it. Okay? So you have to have your NCC dictates everything else, but all the structural levels dictate function. Okay? Draw out lactose.
Yeah. Oh, it's just that would be galactose and glucose. No, I think, yeah.
Galactose is cis or trans?
Cis.
Glucose, cis or trans?
And
What type of linkage is this?
A
1,4 glycosidic linkage. This is carbon 1, 2, 3, 4. Carbon 1, 2, 3, 4, 5, 6, right? So it's a 1,4 glycosidic da 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 da. Okay? If I want to break this bond, I need to have an enzyme. And so in that enzyme, I'm going to have my primary structure, NCC, NCC, so forth, C, okay? And so like that would be the O's. And then there might be another polypeptide chain that's running this way. Okay, so we'll get some hydrogen bonding between those. Well, how this is going to work is there's going to be a R groups interactions, okay? And those R groups are going to hold in place this molecule. And if I can do, say, hydrogen bonding right here, okay, that hydrogen bonding is going to work right there. That's going to allow these electrons to move around. And because of resonance, this hydrogen bond is going to form. This one might disappear for a second. And so what that's going to do is that's going to allow this to break. Okay? And all I need to do is increase the likelihood of it breaking. And so that's what enzymes do. They hold things in place. And so this enzyme is going to have a certain shape that's going to fit this molecule. It's going to have certain charges that are going to bind with the functionality of it. And it's just going to hold it in place. And so ultimately what this does is we have our initial and our end energy state, right? So this is the dimer, lactose. These are our two monomers. Well, in order for that bond to break on its own, it's going to have a high amount of potential energy. It doesn't want to do it. But this enzyme, because it's so big, will take the load of that energy and make it more favorable. So what we're going to end up doing is lowering this down so it's like that. And all that does is it speeds the reaction up. It makes it go faster because we're holding it in place. Does that make sense? Okay. So we spent the last 2 weeks basically getting to the point where we can assemble an enzyme. Okay, so that's why we did all of our biochemistry. That's why we understood protein structure. Now we're going to try to understand how enzymes work. And all enzymes basically do the same thing. If I bring two monomers in, if I stabilize it, I'm more likely to get that linkage to form. We just want to make it more likely to happen. Can it break on its own in nature? Yeah, just fine. But we're going to make it more likely to happen. Okay? We're opening a session.
I picked primary, secondary,
I picked everything but 5.
I picked everything but D and E. I don't know about quaternary.
Well, I think this is multiple polypeptides,
So it's got a,
so it has quaternary structure.
okay.
How many N-termini are here? 4, right? That's one color, that's one color, that's one color, and that's one color.
Oh.
There's 4 N-termini. How many C-termini do we have? 4. How many polypeptide chains? 4. Is this therefore demonstrating primary structure, secondary structure, tertiary, and quaternary? Yes. The only thing that's not correct is there's a single N-termini, because there are 4. What organelle made them? Rough ER, and the polypeptide chain was made by the?
Rough.
There we go. Look at what we're doing. How many mRNAs did it take to make this? 4. Nice. It's a sequence. Don't even look.
Because you see 4, right?
This is my N-termini, right? C-termini. Where do you imagine this one to be, an inside or outside of a cell? Inside. Because hydrophobic or philic? Hydrophobic interactions. Okay? To recap, this is one residue. This is a peptide bond. This is another amino acid residue. Okay? You feel good? All right, let's work on the inside matrix.
Okay.